In this lecture, we are going to discuss the topic Cauchy's integral formula for derivatives. In the previous lecture, we have discussed about the Cauchy's integral formula. The Cauchy's integral formula states that f of z0 is equal to 1 by 2 pi I into integral over c f of z divided by z minus z0 into dz, where f of z is analytic inside and on this simple closed contour C, and z0 is a point inside C. Okay, this is Cauchy's integral formula. Now we are going to state the Cauchy's integral formula for derivatives. This is the theorem which gives Cauchy's integral formula for derivatives. Okay, it states that let f be analytic in a simply connected domain D, and let C be a simple closed contour lying entirely within D. If Z0 is any point within C, then the nth derivative of f at the point Z0 is equal to n factorial divided by 2 pi I into integral over C f of z divided by z minus Z0 power n plus 1 dz. Okay. So by using this formula, we can find this type, contour integral of this type, that is f of z divided by z minus z0 power some power n plus 1, right? So it will be 2 pi I divided by n factorial into the nth derivative of f at the point z0, right? So here also we have we are given that we need to uh, we need the condition that the function f of z, we have the integrand is f of z divided by z minus z0 to the power n plus 1. So we need the condition that the function f of z, that is the function on the numerator, that is f of z, should be analytic inside on in a simply connected domain D, and C should be a simply closed contour lying inside and entirely inside C. Okay. Then we have, and Z0 is in any point inside this C. Then we have this formula. Okay. This formula is called the Cauchy's integral formula for derivative. Okay. That is for derivative at the point Z0. Okay. Okay. We can do a problem. Evaluate contour integral over C z plus 1 divided by z power 4 plus 4z cube dz, where C is the circle, mod z is equal to 1. So here our contour is mod z is equal to 1, that is a unit circle with a center 0. Okay. So here our integrand is z plus 1 divided by z cube plus 4 z power 4 plus 4z cube. This is nothing which is equal to z plus 1 divided by, to find the singularities we can take z cube outside from the denominator. So the z cube into uh, z plus 4, right? Therefore we have the singularities are given by what? The denominator equal to 0. That means z is equal to 0 and z is equal to minus 4. Okay. So we know here z equal to 0 is of order 3 and z equal to minus 4 is of order 1. Okay. So now out of these singular points, we have z equal to 0 lies inside C. C equal to mod z is equal to 1, and the other singular point minus 4 lies outside C, right? So of these, z is equal to 0 lies inside C, and z is equal to minus 4 lies outside C. So we can write this function as z plus 1 divided by z cube into z plus 4 can be written as z plus 1 divided by here z equal to minus 4 is lies outside the circle, outside C. So we can take the corresponding factor can be included with f of z. So z plus 1 divided by z plus 4 whole divided by z cube, right? So in that case, now choose or put f of z is equal to z plus 1 divided by z plus 4. Here here this function f of z is if you take this as f of z, this is analytic, not analytic only at the point z equal to minus 4, but that point is outside the circle. So we have this function f of z is analytic inside and on C, right? So put f of z equal to this, and z naught is equal to this is z minus whole cube, so z naught equal to 0 in Cauchy's integral formula. That means Cauchy's integral formula we have, okay, we have the conditions are satisfied because this function is analytic inside and on C, because the only singularity is at z equal to minus 4, but it's like this z equal to minus 4 lies outside C. So yeah, we are taking only this as our f of z, right? So we have fn of z naught is equal to n factorial divided by 2 pi I in integral over C f of z divided by z minus z naught to the power n plus 1 dz. This is our Cauchy's integral formula now. Now we have to replace f of z by this, and z naught equal to 0 and n, as we need to find the integral of this, right? This is actually our integrand. So this is z minus 0 whole cube, so n plus 1 should be 3. So here also we need to take n equal to 2 and n equal to 2 in Cauchy's integral formula. So n equal to 2 means we will have here n plus 1. So therefore f the second derivative of f at the point 0 is equal to n factorial, that is 2 factorial divided by 2 pi I integral over C f of z is this f of z is z plus 1 divided by z plus 4, that is z plus 1 divided by z plus 4 is f of z divided by z minus 0 whole cube, that is z cube dz. This is actually, this is our required integral. So this implies we have integral over C z plus 1 divided by z cube into z plus 4, that is our required integral, is equal to 2 pi I by 2 factorial is 2, so this is pi I only, 1 by pi I only. So pi I into f double dash of 0, but we know that f of z is equal to z plus 1 divided by z plus 4, right? So from that we can will get uh, since f of z is equal to z plus 1 divided by z plus 4, we have f dash of z is equal to, by quotient rule we have z plus 4 into derivative of z plus 1 is 1 minus z plus 1 into derivative of z plus 4 is also 1 divided by z plus 4 power 2. So this is z minus z, so 4 minus 4 minus here so we have yeah z minus z plus 1, so here 4 minus 1 is 3, right? 3 by z plus 4 whole cube whole square. This is f dash of z. Now what about f double dash of z? F double dash of z is nothing but minus 6 divided by z plus 4 whole cube, right? So we have this is equal to pi I into f double dash of 0, that is minus 6 divided by z plus 4 whole cube, that is 4 cube. 4 cube is 64. So minus 6 by 64 minus 6 pi I by 64. This is nothing but uh, minus 3 pi I divided by 32, right? Minus 3 pi I divided by 32. This will be the value of the integral. Okay. So if we have a singularity with more than one, with order more than one, or then we can apply this Cauchy's integral formula for derivatives. Okay. Now we have another question. Evaluate is it integral over c z cube plus 3 divided by z into z minus I whole square dz, where c is the contour in the figure. So here we are given this contour. Contour is this, like this. Okay, this is our contour. From this figure, it is clear that this contour C is not simple closed contour, because here this contour is closed here, right? So this C is not simple closed contour, but we can consider this C as a union of two simple closed contours. One is this, and the other is this one. So we can uh, denote this as C1 and this as C2. That means C1 is this. Okay, this contour, this is a simple closed contour which is C1, and C2 is this simple closed contour, this, right? Okay. Now considering our function, the integrand is z cube plus 3 divided by z into z minus I whole square, right? So clearly it is not analytic at the point. It is not analytic at the points z is equal to 0 and z is equal to I. Okay, so z is equal to 0 and z is equal to I. So checking these points, we know this z equal to 0 is here and z is equal to I is here. So if we are consider C1, okay, if we are consider C1, then we can exclude, that is if z equal to 0 lies inside C1 and outside C1, z equal to I lies outside C1. Okay, now if you are considering C2, we can say that z equal to 0 lies outside C2 and z equal to I lies inside C2. Okay, so by using that, we can write this integral, the given the recurred contour integral, we can write it as integral over C z cube plus 3 divided by z into z minus I whole square dz, which is equal to integral over C1 z cube plus 3 divided by z into z minus I whole square dz, plus integral over C2 z cube plus 3 divided by z into z minus I whole square dz. Okay, so we can write this integral over C as integral over C1 plus integral over C2. Now the orientation of C2 is positive and the orientation of C1 is negative. Okay, because this is like this. So this is a clockwise direction. So this is negative orientation. So we can write this integral as negative integral over C1 z cube plus 3 divided by, here we can here we know z equal to 0 lies inside C1 and I lies outside C1, right? So we can write this integrand as z minus I whole square all divided by z dz. Okay, that is this is f of z and this is z minus 0. So plus integral over C2. Here on C2 we know z equal to I lies inside C and lies inside C2 and z equal to 0 lies outside C2. Right. So we can rewrite this integrand as z cube plus 3 divided by z whole divided by z minus I whole square dz. Okay, so this can be written as minus I1 plus I2, where I1 is this integral and I2 is this integral. So we can separately evaluate these integrals. Okay, now number this as 1. So for I1, to evaluate I1, so here we can use the Cauchy's integral formula. We have by Cauchy's integral formula, Cauchy's integral formula is f of z0 is equal to 1 by 2 pi I into integral over c or c1 f of z divided by z minus z0 dz. Okay, so to use this, we can put, we know z equal to 0 lies inside c1, and f of z equal to this. If you are taking f of z equal to z cube plus 3 divided by z minus 1 whole square, then this will be analytic inside and on c1, right? Inside and on c1, because the only point at which this function is not analytic is 0. So we have excluded that factor. Okay, we have excluded the factor z minus 0. So so put f of z is equal to z cube plus 3 divided by z minus I whole square, and z naught is equal to 0 here. So here z minus z naught is equal to z. Okay. So therefore we have f of 0 equal to, from this f of 0 equal to 1 by 2 pi I into integral over c1. F of z is z cube plus 3 divided by z minus I whole square divided by z minus z naught. Z minus z naught is z minus 0, that is z, that is would be here into dz, right? So we have this integral is nothing but this is I1, right? So this integral c1 is, say, integral over c1 is z cube plus 3 divided by z into z minus I whole square dz is equal to 2 pi I into f of 0, where f of z is equal to this. Okay, so which is equal to 2 pi I into f of 0 is 0 plus 3 divided by 0 minus I whole square. So 0 plus 3, 0 minus I whole square. So this is nothing but 2 pi I into 3 divided by I square. I square is negative 1. That is minus 6 pi I. Right. So this is I1, right? Now I2. For I2, we know I2 is this integral over c2, right? C2 z cube plus 3 divided by z minus I whole square. So over c2 we know that I lies between lies inside c2 and 0 lies outside c2. So we have taken like this, right? So in this case we can choose f of z as z cube plus 3 divided by z, and z naught as I, and we can use the Cauchy's integral formula for derivatives, because here we have z minus I whole square, right? So for that, for I2 is actually integral over C2 z cube plus 3 divided by z minus I whole square, right? So we need to find this. So for this we can use Cauchy's integral formula for derivatives. Okay, that is f n z naught is equal to n factorial divided by 2 pi I integral over c or c2 f of z divided by z minus z naught power n plus 1 dz. So comparing this integral with this integral, we can put f of z as z cube plus 3 divided by z. Okay, this can be taken as z, f of z, and z naught as I, right? So we have this implies, this formula implies we have, and n equal to, we have here is z minus 1 whole square here. So but here z minus z naught, then power n plus 1. So n plus 1 is equal to 2, so n equal to 1, right? So we have f dash of z naught, this is n equal to 1. So f dash of z naught, where z naught is I here, z naught of I is equal to uh, n factorial, that is 1 factorial divided by 2 pi I into integral over c to f of z is this z cube plus 3 divided by z whole divided by z minus z naught power n plus 1, that is z minus I power n plus 1 is 2 dz. Okay. From this we have integral over c to z cube plus 3 divided by z into z minus I whole square dz is nothing but 2 pi I into, this is one factorial, that is 1, so 2 pi I into f dash of I, where f, so to apply this we have to find f dash of z. Since f of z is equal to this, we have f dash of z is equal to by quotient rule, by using this, so z into derivative of z cube plus 3, that is 3 z 3 into derivative of z 1 divided by z square. Okay, so this is 3z square, 3z cube, that is 2 z cube minus 3 divided by z square. Okay, therefore 2 pi I into f dash of I is nothing but 2 into I cube minus 3 divided by I square, right? So this is equal to 2 pi I into 2 into I cube is I square is negative 1, so negative I minus 3 divided by I square is negative 1. So here we have just multiplying this, we get minus 2 pi I into minus 2 pi I into minus 2i minus 3, right, which is equal to 4 pi into I square is negative 1, so minus 4 pi plus 6 pi I. This is our I2. Yes. So we have our required integral is from equation number 1 we have, yeah, integral over c, this integral is nothing but minus I1 plus I2. So we have from equation number 1 the required integral over c z cube plus 3 divided by z into z minus I whole square dz is equal to minus I1 plus I2. Where, so I1 was, yeah, this is minus 6 pi I, so this is minus I1 is 6 pi I plus I2 is minus 4 pi plus 6 pi I, which is equal to minus 4 pi plus 12 pi I. Okay, so we can take 4 pi outside, so this is equal to 4 pi into minus 1 plus 3i. So this will be the required integral. Okay, next we have another theorem, Liability's theorem. Liability's theorem states that the only bounded entire functions are constants. Only bounded entire functions are constants. Okay, that means every bounded entire functions are constants. Okay, next we have a fundamental theorem of algebra. This theorem states that if p of z is a polynomial, is a non-constant polynomial, then the equation p of z is equal to 0 has at least one root. Has at least one root. Okay, that is, the fundamental theorem states that if p of z is a non-constant polynomial, p of z is a non-constant polynomial, then the equation p of z equal to 0 has at least one root. So to prove this theorem, we can use this Liability's theorem. Okay, so suppose that let us suppose that P of Z is not equal to 0 for all Z. Okay. If possible, suppose that P of Z is not equal to 0 for all Z. Okay. Then then we can define another function, or then function f of z is equal to 1 by p of z. Since p of z is not equal to 0 for any z, we have 1 by p of z is entire function. It's an entire function, right? Therefore f of z is an entire function. Now also we have from this f of z is equal to 1 by p of z. So we have, as mod z tends to infinity, we have mod f of z tends to 0, right? Because this is p of z is not equal to 0 for any z in the complex plane C. So as z mod z tends to 0, we have mod f of z tends to as mod z tends to infinity, we have mod f of z tends to 0. That means this function f of z is bounded for any finite values of z. Okay. Therefore, we have function f of z is bounded for any finite z. Okay. Therefore, we have f of z is entire function and f of z is bounded. So, by Liouville's theorem, we have Liouville's theorem, the bounded entire functions are constants. So, we have f of z is a constant function because f of z is entire function and it is bounded. Okay. Therefore, by Liouville's theorem, f of z is a constant function. So since f of z is equal to 1 by p of z and f of z is a constant function, therefore p of z is also a constant function. But it is a contradiction because we are assumed that we are given that p of z is a non-constant function. Okay, which is a contradiction. To the fact that p of z is a non-constant function. So that means our assumption is wrong. Our assumption was p of z is not equal to 0 for any z belongs to C. Okay. So this assumption is wrong. Okay. Therefore, our assumption that p of z is not equal to 0 for any z belongs to C is wrong. Therefore, p of z is equal to 0 for some, that therefore there exists some z belongs to C such p of z is equal to 0. Okay, that means p of z is equal to 0 has at least one root. Okay, that is p of z is equal to 0 has at least one root.